Hello, and welcome to Edexcel Demola, and today's video we are starting Module 5 in Chemistry, Rate of Reaction. So we're going to go through orders and some graphs, but no time to waste. Let's get straight into the video. Okay, so let's talk about rate of reaction. And this is the changing concentration of reactants or products divided by time. You can see that we've got a nice equation underneath. So rate is equal to the changing concentration divided by time. And we also have our units. This is things that we covered in, I believe it was Module 2, which is why we're kind of rushing through it. Now, what's actually new when we get to Module 5 is this idea of order. So, we have three that you need to know for your exam. Zero order, being that the rate is independent from the concentration of the reactant. We could make the reactant like 10 times bigger, it would have no impact on the rate. Cool. First order is that the rate is directly proportional to the concentration of the reactant. What I mean, if we double it, the rate doubles. If we triple it, the rate triples. It's just like that. Second order is a bit different. It's that the rate is directly proportional to the square of the concentration of the reactant. So now we're saying if we double, then it's going to be 2 squared 4. If we triple the concentration of the reactant, then the rate is going to be 3 squared 9. It's going to increase by 9-fold. So those are considerations that you need to have into account. Just know we can also have this with fractions. So for example, say we half something and it's second order, a half squared is a quarter. And then you'd say that the rate is going to decrease by a factor of 4. Cool. Overall orders is another concept you need to know. It's literally just the sum of all the orders in the rate equation. So let's say, for example, we've got a first and a second order, then the overall order is 3. Cool. And we're going to talk a bit more about rate equations coming up shortly. So what you see here is graphs. You have rate concentration graphs, and you need to be able to look at this and identify what order is my reactant, right? So zero order, you can see we just have a straight line. Yeah. So because we have a straight line, that's showing you that the concentration increasing has no impact on the rate. Cool. First order, you can see that linear, directly proportional relationship. So you can see that the concentration and the rate are increasing by the same amount. And now second order, you have a curve. So that's going to represent how it's going to be directly proportional to the square of the concentration. Cool. But just remember these graphs, they do come up. Now, your rate equation is something that we're going to sit with a bit longer, coming up in the next slide. What you should see is we have a reaction, A plus B goes to C plus D, and the numbers in front, the M and N, is just meant to represent the stoichiometry. Now, our rate, when we're making a rate equation, we say rate is directly proportional to the reactant to the power of whatever number's in front of it, times the other reactants to the power of whatever in front of it. Just know that not all reactants are going to be in the rate equation as well. Now, because we are directly proportional, if you're a mathematician, you would know that we can have rate constants, this idea of a constant, right? So we're going to say that the rate is then equal to the rate constant, which is going to be K, multiplied by the concentration of A to the power of M and B to the power of N. Cool. So take all of that into account as we move into actually calculating the rate constant. Okay, so we've generated this question, which is an example of what you might expect to see in exam. So you can see they've told you that the rate equation is A times B, whatever. And then you also have experimental data. This is a really, really common question. So what you're going to do is you need to make comparisons. So let's see. Experiment 1 is kind of your default most of the time. It's going to be what you refer to. And what you can see, what's changed between experiment 1 and 2? Well, let's use red. You can see that the concentration of A has doubled. The concentration of B has stayed the same. So we're going to use that. Let's go here. So we can say the concentration of A doubles. And you can see here the rate has also doubled. And because of that, concentration double, rate doubles. We're saying that A is first order. We're happy with that. Now let's look at 1 and 3. So again, be very careful, be very cautious that A hasn't changed as well. So A has stayed the same, B has doubled. Cool. So we know B has doubled. We can see from the rate, it went from 2 to 8. So what does that tell you about the rate? The rate is increased by a factor of 4. So you can see here, between, that should say experiment 1 and 3, you can see that the concentration of B doubles, but the rate increases by a factor of 4. So 4, the square root of 4 is 2. So we're very happy to say that B is second order. That gives us our rate equation now. So rate equals K lots of concentration of A times concentration of B squared. Now, sometimes you end it off there. Other times I want to get you a value of K. So to do that, literally what we're going to do is we just sub in values. So I just say it's easiest to use whatever simple, in this case reaction 1, where both for the concentration of 0.1, rate is 2. So again, be careful about standard form because that catches people out. But you can just sub it in the values. If you rearrange this for k, if you've done maths, that should be a bit more simple for you. But you'll see that it's going to be 2 times 10 to the minus 3 divided by the 0.1 times the 0.1 squared. And that's going to give you a value of 2. Okay, so we're happy to say that k is 2. But we also need to think about the units. This is another question they ask, or it's going to be part of the same question because you can typically get like 6 markers on this. So in terms of getting the units, we just need to think, okay, go back to what we had here. This was the rate on the top. I'll draw a dot next to it. That's the rate. And these were the concentrations. So use the units that we know. So we know that rate is mole per dm cubed per second. And we know that concentration is just mole per dm cubed. So when you have that, we can see that we can cancel these out because they're the same. So you have s to the minus 1 over mole per dm cubed squared. Now again, if you know maths, you know that what we can do to bring this to the top, the mole per dm cubed, is just to literally just to do it and then bring it to the top, essentially, because it's the same as this, is what I mean. That's what we have at the bottom, basically. So then we just times everything in the bracket by minus 2. So that's why now minus 3 times minus 2 is 6. So dm to the power of 6. And then the mole is now just going to be to the power of minus 2. And then you have second at the top. Don't need to do anything with that. S to the minus 1. So this is typically how you're going to leave your units there. And then you can put it all together and say the value of k is 2 dm cubed to the 6 mole to the minus 2 per second. Hope that makes sense. If you need to go back through it, please do. We do have another example of something like this in the questions. Okay, before we finish things off, we just need to talk about concentration time graphs as well. So for this one, you actually don't need to know second order. You just need first and 0. So you can see here that the rate of reaction is staying constant because we've got a graph just going down. The gradient stays the same. So that's how you can tell it's 0 order from the concentration time graph. But as you know, as the reaction goes on, the concentration of the reactant is going to fall. So that's what you can see in this graph. Now, first order is a bit different. You have a graph, you have a curve that starts to plateau, right? And we need to talk about something special about that curve. It's that it has a constant half-life. What do I mean? So if we just annotate the diagram, say, for example, that this is where we were half of what we had from the start. So that's going from the start. And then let's say that now half of that is here, right? Again, we're just doing rough. What we're saying is that the gap between here and the gap between here is the same time period, right? And that time period is what we're going to call our half-life, right? So the half-life remains constant all throughout that graph for a first order reaction. Bog standard definition for half-life is time taken for concentration of a reactant to half. That's just something that you need to know for your exams. And you should know as well that the rate constant can be found using half-life. I am not too sure if you get this in your formula book, but rate constant is equal to ln2 divided by half-life. And ln2 is just a button that you can find on your calculator. So you'll find the ln button. It will look something like that on your calculator. And you just put 2 inside the bucket when you're putting it in. Now, in terms of calculating the initial rate, we just need to know about how do we actually do it. So this is all good, but remember, we're normally using experimental values. So the experiments usually involve something called continuous monitoring, which is essentially that you're measuring the concentration, or you're taking something, you're measuring it at set intervals during the whole course of the reaction. Cool. And we can do this with colorimetry, volume of gas, or mass loss. I think you can also do it with titration, but I wasn't too sure on putting it in, but let's add it. But you can do continuous monitoring of this. So you're literally just measuring something as it goes throughout the reaction, put it into a graph, and then you'll find your rates of reaction at different times. Okay, it's question time, so I'm going to make sure you can see these. So we're saying that questions about hydrogen peroxide, that's the first bit. And you can see we've got a bunch of data, and you need to find what the rate equation is using the rate constant. Next question, again, is very similar. You need to find what the rate constant is. And then finally, you need to conclude why in this reaction for number 9 that hydrogen ions are not a catalyst. So I'll let you get to it. Okay, so now going into the answers, we need to be very specific about which experiments we pick. So you can see here, we're trying to find the rate equation, right? So we need to think, when are things staying the same and when are things changing? So if you follow my lead, look at the red first. You can see in experiment 1 and 2, everything stays the same except the concentration of iodide ions, which doubles. So iodide, I minus, is doubled, and you can see the rate has also doubled between experiment 1 and 2. So we're going to say that concentration of iodide ions is first order. Now, let's look at experiment 1 and 3. So in experiment 1 and 3, you can see that the hydrogen peroxide doubles, but you can see everything else stays the same. So we say that hydrogen peroxide doubles, and what happens to the rate? Rate also doubles. So because the rate has doubled, we can say the concentration of hydrogen peroxide is also first order. Now finally, let's look at the purple. So unfortunately for the proton, you can see that there's actually no equation where this is the only one that changes. So we need to make do and go with experiment 1 and 4. So looking at experiment 1 and 4, you can see, yes, the concentration of your proton does double, but you can also see that the concentration of hydrogen peroxide has also doubled. Now let's see what happens to the rate. Rate doubles. So let's use that information properly. Now, we know that the concentration of hydrogen peroxide is first order. We've already determined it. So if that's gone up by 2, we know rate will go up by 2. Now, is there an effect from the proton or the H plus ion? No, because the rate has only gone up by a factor of 2. So you can say that the concentration of your H plus is 0 order. And that will help us to get the rate equation, which you will see in this slide. So you can see rate equation is K concentration of hydrogen peroxide, concentration of iodide, right? You do not need to include something if it's 0 order in a rate equation, because anything to the power 0 is 1. Now, in terms of determining the value of K, you can see, I think they just used experiment 1 probably, and you just sub in the values and you get your answer. Now for deriving the units, you can see here, again, when you rearranged it, your rate, mole per dm cubed per second, is over concentration of one of the reactants and concentration of another reactant. So what you would do, cancel this out, and then you can see, now we have mole per dm cubed to the minus 1, s to the minus 1, and then you can just change the bracket. So that's why it's dm cubed mole to minus 1, s to minus 1. Cool. Now, what we need to do is look at this one. So fortunately, we do have something very similar. It is the same reaction. So when you're doing this, you're literally following the same steps. I might kind of jump things just to make it a bit easier. What you'll see, experiment 1 and 2, you can see that the rate doubles, and you can see concentration of hydrogen peroxide doubles. Hydrogen peroxide is first order. You can see, if we now look at the yellow, you can see in terms of the protons, you can see that doubles. Thankfully, every other concentration stays the same between experiment 2 and 3, but the rate stays the same, which tells you that the proton is 0 order. And then finally, with the iodide, you can see, okay, so iodide doubles, right, between 2 and 4, but also between 2 and 4, peroxide also doubles. So we know there's already going to be a factor of 2, but then the other one to make a factor of 4 that increases by is because of your iodide. So that will tell you that iodide is also first order. Once you've done all of that, we literally do the same thing in terms of choosing any of the experiments, put in the values, then you should get a value of the rate constant. Just note it said 2 significant figures, and it also said in standard form and with units. So those are things that can catch people out if they don't read it properly. Now finally, it said the student concluded that protons act as a catalyst. Why are they not correct? Now, some people will jump straight to saying that protons aren't in the rate equation, right? Which is true, but also that is not the reason why they aren't a catalyst. If we go back and look at the question, you can see that the hydrogen ions are actually taking part in the reaction. So if we also had the 2H plus on this side, we'd say, okay, fine, it's a catalyst. But because that's clearly been used up, we can say that it's not a catalyst if we think back to what the definition of a catalyst is. Okay, so now we can get into the A-star tips. So I am such a big fan of definitions. Please, there's such easy marks when it comes to exams, so just memorize all the definitions you possibly can. So rate of reaction, rate equation, rate order, and also half-life are important ones for this, and knowing their different equations. So it's especially like that K equals ln over half-life, easily forgotten. Recognizing the graphs, so your concentration time, your rate time graphs, just be able to recognize them for 0, first, second order. You don't need to go into like third order and everything like that. It will not come up on your exam unless they're asking you something like get the overall order, pretty much. Experimental data, you need to be really confident with going through those tables and analyzing. Like, really look closely to see what are the changes between experiments so that you don't get caught out or anything like that. But it's a very common question. I almost guarantee it will come up pretty much. So make sure you are prepared for that. And then also understanding practical methods of determining the initial rate of reaction. So I know we haven't gone into them too much in this video, but they can definitely ask you about designing an experimental technique that will help you to find the initial rate. So be very prepared to go through like your colorimetry, your titration, mass loss, and volume of gas, because it can come up. What not to do. So tangents, honestly, I know we haven't had to draw any, but so many people get tangents wrong, it's annoying. So use a ruler, first of all. Some people don't even use a ruler. But use a ruler and try your best to only hit the graph once. That's what a tangent is. It only hits the graph at one point. So make sure that you're only really hitting it at the point that you need, the time that you need. Now, also, not looking carefully at the data. So, like, they do a lot of things to catch people out. So, it will be, like, subtle changes, like changing the standard form. So, like, I think we saw it in the question that one of them was -6 and the other one was -5. I didn't point it out there, but that catches people out. So, make sure you are looking very carefully. And then also about multiple reactants changing. We definitely saw that in the second question that we did. So, be very careful because they do that to throw people off. And then also just assuming all reactants will be in the rate equation. So like some reactants, if there's zero order, there won't be. If they're not in the rate determining step, there also won't be. Rate determining step will be next week's video. So thank you so much or the next chemistry video. So thank you so much for listening. If you found it useful, please like and subscribe to the channel. Any questions at all, A-level chemistry, about rate of reaction, pop them in the comments below and I'll do my best to answer. We've also got a TikTok and an Instagram, both at demola. Links will be in the description below. But that's all for me for now. So thank you so much for listening, and I'll catch you in the next one. Bye for now.